Okay, two polynomial functions of a higher degree, and so in this case we're going to be talking about something higher than x squared, right? And so again, we're talking about the degree of our polynomial function is going to be the largest exponent you can find. But before we get to that, there are two important things that have to happen for a function to be a polynomial function, right? So we can have functions that are not polynomial functions, but to be a polynomial function, first thing we got to be continuous. All right, so graph A works because I could draw this without ever picking up my pen, whereas B is a piecewise function, and right here, oh, I got to pick up my pencil to go over here and keep drawing it. So A, yes, B, no, not a polynomial function. Rule number two, gotta be smooth. All right, so on this one, we look at this. We never have any hard edges, no hard points. It's always a nice curve to it, as opposed to our absolute value, boom, right there. That's a hard, non-smooth, sharp turn. So again, nice rounded turns. Yes, we're polynomial, polyfunction. And over here, this would be no because of this point right here. All right, so once we have that, we can take a look at some power functions. And so what this is saying, you can see the light line here is y squared down in here. This darker one is x to the fourth, and they have the same shape, but as we get bigger and bigger exponents, larger degrees, as we get in between -1 and 1, we're going to get a lot flatter. And once we get outside of that, you can see we're going to take off a lot steeper. And that works with odd ones as well. You can see x to the fifth is steep, but then shallower as we get inside of ones. All right, so we can use that to compare the original functions, x cubed or x squared, with larger power functions. All right, so let's do a quick sketch of these. -x to the fifth on this one. I'm going to make these kind of large so we can see the flattening effects. Negative, we know we're going to go down, and normally we're going to cross right here. And normally with x cubed, we're going to hit right here 1 and -1. I'm just going to draw in the nice x cubed graph. This would be x cubed. And so I want something steeper, flatter, and then steeper again. So that's just a quick sketch. It's not perfect, but the goal is we're doing compare and contrast for where we're flatter and where we're steeper. So same thing here. This is x plus 1, which means our vertex is over here. Normally, my parabola would come in like this. This is my x squared. And so x to the fourth is going to be a lot steeper. Okay, like that. All right, so your job here, use the same thinking on number 17. Think about your transformations and then what kind of steepness we have. All right, second thing we need to learn in this section is the leading coefficient test. And the leading coefficient tells us about the endpoints of graphs. And here's what we're looking for. When we're odd, x cubed, x to the fifth, x to the seventh, depending on our function, we might have all sorts of stuff going on in the middle, but at the ends, we're going to be going in opposite directions. If we're odd, we're going to be going in opposite directions. Think about the graph of x cubed. Looks like this. On the left, it's going down. On the right, it's going up. All right? So if it's odd, it's always going in opposite directions. And think about this one, x cubed. We start low and go high. That's what we're saying here. If we have where is it? There we go. If our coefficient is bigger than 0, meaning positive. So if we have a positive here, we're going to start low, finish high. If we have a negative x cubed or x to the fifth or anything like that, start high, finish low. Same thing applies to even functions, but in this case, if we're even, like x squared, our ends go in the same direction. Positive, both go up. Negative, both go down. We don't know what's going on in the middle. All sorts of things could happen, but on the ends, we're going to be going in the same direction. All right, so the question that's going to be asked is describe the left and right hand behavior of these graphs. So this is, I don't care about 4x at all. I'm just looking at the largest exponent. Our degree is 3, and it's a negative. So I know it's got to start high, finish low. Okay? On this one, I don't care about any of this. I'm just looking at x to the 4th. Since it's positive, I'm going to start high, finish high. Okay? This would be our left-hand behavior. This would be our right-hand behavior. Right? Just as like if you put your hands right on the graph, left hand and right hand. And finally, x to the 5th, we don't care about that. It's going to start low, do some things, and finish high because it's a positive. Okay? And so you need to see if you can tell me what's going on 23. All right, zeros. To find our zeros, remember we're going to make f of x equal to 0. All right? And so this slide says how many could we have? We have at most n real zeros, where n is the degree. So if we have x to the 4th plus 3x cubed minus 5x squared, our degree is 4. So we have at most 4 zeros. Could have 2 or 3, maybe 1, maybe it never crosses, maybe we have none, but we can't have 5. Right? At most 4 zeros. And it turns n minus 1. It turns at most 3 times. At most 3 turns in our graph. Right? So if we have x to the 4th, it's going to look like this. It could be flat. Or what if we had this one? Here's our turns. There's a turn, there's a turn, and there's a turn. Couldn't do any more turns than that. 3 is the most we could possibly have. All right, and so a couple different ways of talking about zeros. X equals a, when we have it inside with our x in here. A is the 0. So if we can isolate these factors, a is one of the zeros, right? And so that's essentially what everything else on this slide is saying. Also that a is one of the x-intercepts. Remember, zeros are where we cross the x-axis. So let's find all the real zeros of this equation. So our job is we're going to factor everywhere we can. So on this one, let's pull out a 2, and we'll pull out a negative 2, x squared, and we're left with x squared minus, it's going to change the sign, and just 1 in here. All right, we can factor one more step. Negative 2x squared, x minus 1, x plus 1. And so we have a couple of zeros in here. We've got 1. We've got, remember this is minus negative 1. So we've got negative 1, so x equals 1, negative 1. And from in here, that's going to be just 0, because we could say negative 2x squared equals 0. Solve for x. We only have 3 zeros. Is that okay? Yep, we can have 4 at the most, so 3 is okay. Let's find the number of turning points of the graph. So on this one, we could have at most 3. All right, and on this one, let's think about our graph. We have an intercept at 1, at 0, and at negative 1. And we're going to finish, since it's a negative, low and low. So we're down here, and we're down here. How could we possibly touch all 3 of these intercepts? Well, we could do something like this. All right? So we could have 1, 2, 3 turning points on there. Is there any other way to draw this so that it touches all 3 and has the appropriate turning points? No, there's not. So this is 3 turning points. All right? You can verify that by putting on your graphing calculator, and I would definitely do that if you were unsure about any of these problems. Get them in your graphing calculator to check. All right, so use 35. Use the same thinking. Tell me all your zeros. Tell me the multiplicity of each 0 and the number of turning points, and then graph it on your graphing calculator to verify. All right, so it kind of came a slide early, but let's talk about repeated zeros. I think we all know about this. But just a reminder, if we have x minus 1 squared, multiplicity is 2. I'm going to touch at 1, I'm not going to cross at 1. I'm just going to touch. As opposed to if I have x minus 1 cubed, an odd, then at 1 I'm going to change my slope and flatten out, but I'm going to cross. Okay, so that's what multiplicity does. And so that'll be important in looking at some of these graphs, such as number 4. All right, so 4 and 5 are the hard ones. These are the ones, not necessarily hard, but the most work. We want to be able to sketch by hand graphs of polynomial functions. So here's the steps we're going to use. We're going to apply the leading coefficient test to figure out our edges. We're going to find all our zeros. Then we're going to plot a few additional important points to figure out all our curves. And then we'll draw the graph by just connecting our curves. So let's start on this one by talking about our end behavior. So leading coefficient test, it's even and it's positive. So I know the ends of my graph are going to be like that. Same direction, both pointing up. All right, let's talk about zeros. So 0 equals, we can pull out an x cubed, and we're left with 3x minus 4. So x equals 0 from the first one. Let's make a dot. And on the next one, 3x equals 4. So x equals 4/3, or 1 1/3. So right in here somewhere. Okay? And so now we need to ask ourselves, how are we going to possibly touch those, right, on this one? And so let's talk about our multiplicity. At 0, we have multiplicity of 3, so that means we're going to be coming through here, kind of changing direction, okay? And then we're going to need to come back through it here, like that. So the important thing is down here we must have a minimum value down at the bottom, okay? So on this one, we're just going to guess at what our minimum is, and then we're going to use our graphing calculator to go trace it and find it, because we haven't yet learned how to figure out what the minimum is unless it's x squared. All right, but that's what our graph's going to look like. We've got to label our important points. So this is 4/3, 0. This one here is 0, 0. And let's go use our graphing calculator to figure out what our minimum is, and also to verify that our graph looks like it should. So I'm going to plug this in, 3x to the 4th minus 4x cubed, and let's go ahead and graph it. And there it is. All right, I'm going to go ahead and do a box zoom to get in on that close to 1 section. Okay, so as we can see, here's where it's flattening out because it's an x cubed, and we want to find our minimum here. So let's use our calc feature, and we'll find a minimum. Left bound, it's already in a good spot. Hit enter. Let me go to the right of it just a little bit. Hit enter. And then guess, let me think right where I want it to be. Hit enter. And it looks like 1, -1 is our 0. So we'll come back to our graph and label this 1, -1. All right, all the important pieces are on our graph, and we are ready to go. So remember, 4 steps: leading coefficient test, zeros, additional points like minimums or turns, and then we draw it. So do that on 75 and make it look nice and pretty. All right, one more example for me to show you on this one. So leading coefficient test, negative and odd. So that means we're going to start high and finish low over here. And let's find all of the zeros of this thing. So we do have an x, we can pull that out. And I'm going to pull the -2 out also. And we'll be careful about our signs. So this becomes x squared minus 6x plus 9/4. Since we took a 2 out, we divided it by 2. 9 halves divided by 2 is 9/4. So we've got that one, all right? And so on this one, what could we possibly do to find some zeros? Remember that we did in the last chapter. We can, hopefully you said complete the square would be one tactic to go at this, right? Or we could use something that we haven't talked about in a little while, set that equal to 0, What about good old friend the quadratic? So over here, x equals negative b plus or minus square root of b squared minus 4ac. Oh, look at that. The 4's are going to cancel. Oh, lovely. All over 2a. And so we've got 6 plus or minus the square root of 36. 4's cancel. Minus 9. All over 2. 6 plus or minus the square root of 36 minus 9 is 27. All over 2. Okay, and so we could clean this up and have 6 plus or minus 9 goes into that, so 3 root 3 all over 2. So those are going to be our zeros. We've got a 0 at the origin here. We've got one at 6 plus root 3 root 3 over 2. Let's figure out what that is with our graphing calculator. 6 plus 3 root 3 divided by 2. 5.59, so 5.6-ish. 1, 2, 3, 4, 5, right about in there. And 6 minus 3 root 3. Divide that by 2. And we've got 0.4, so another 0 right in here. Okay, and so we know that things are going to have to go like this. So we're starting up here. We're coming down. All right, we're going to turn. And we're going to have to turn again on this one. How many turns do we have? 1, 2. That's absolutely allowed, so that's going to be fine. So we need a couple more points in here. We need our mins, and we can go to our graphing calculator to find that out. Let's go ahead and plot this thing. Y equals negative 2x cubed plus 6x squared minus, I'm going to just put it in as a decimal for time, minus 4.5 x. And we'll go ahead and graph it. Well, I'm already got a nice box zoom in there. And let's see if I made a mistake on here. I certainly may have. So it looks like we just have 1 right here, so this should be a double up right here. So I must have made a mistake. Let's check and see what we've got here. B plus or minus square root of b squared minus 4ac. Not seeing it. Let's go to the old textbook. See where I made a mistake. All right, we can pull this out. Come back, slideshow. So on this one, aha, there's my problem. Didn't decide to divide by 2. Silly mistake. That should be a 3 right there, not a 6. So this should be 9 in the middle. Let me clean this up. Forgot to factor out my 2, so that should be a 3. And so 3 squared is 9, and 9 minus 9 is 0, square root of 0. And this shouldn't be a 6 either. This should be a 3. And so we're going to have 3 over 2. And let's see if that's where we end up. Graphing calculator. Trace. I'm just going to move over, see if this is 1.5, which it looks like it will. Yeah, there we go. All right, good. So, perfect example. Using your graphing calculator to check your mistakes, we should end up with 1.5 here. And it should just touch. So let's get rid of this entirely. Redraw it. Important points at 0 and 1.5. I'm going to come down, touch, and turn the other direction. Still need our minimum down here. Let's trace and find it. Second calc. Minimum. Got to move to the left of it. Got to move to the right of it. And back on the guess. And it looks like 0.5, negative 1. Down here, 0.5, comma, negative 1. This point was 1.5, comma, 0. And this important point here was 0, 0. So we've got all of our points. Sorry about that mistake, but sometimes it happens. We've got to clean up our work, and we use our graphing calculator to check our errors. So see if you can do it all in one try on 77. If it takes you a second try, don't worry about it, and we will go over these. One more thing to look at here, the intermediate value theorem. And this is seemingly a really simple thing. What this says, if we take 2 points, A and B, right? A and B are our x values, okay? And we're going to get a y value that matches up with them, f of A and f of B. If C is in between A and B, right? C is in between A and B, then f of C has to be in between f of A and f of B. That's all this is saying. But it ends up being very, very useful for a couple of different things, such as, sorry, let's flip into the next slide, such as figuring out where the zeros are. So what this long paragraph says in here is that if we can find a point where the y value is positive, and if we can find a point where the y value is negative, the 0 must be somewhere in between that, right? Because to go from positive down to a negative, we must switch past 0, which means that to find the zeros, our 0 must be in between negative 1 and negative 2. And so we can start to zoom in on what our zeros are. All right, so we're going to use that to approximate the real 0 of this. And we're going to use our graphing calculator for these problems. So we're going to go back in here to the y equals and clear it up and go x cubed minus x squared plus 1. And on these, we're going to go to the table. So I'm going to do my table set first, and I'm going to start with something negative and count by ones. And then let's go to the table and see what happens. And what I'm looking for is, when does the y value switch from negative to positive? And there it is, between negative 1 and 0. So I know that my zeros for this problem must be between negative 1 and 0, because that's where it went from negative to a positive. So I want to get closer to that. I want to see exactly when it switches. So now I'm going to change my table set from negative 5 to negative 1, and I'm going to start counting by point ones. Really zoom in on this thing. All right, and so when does it switch? It switches between negative 0.8 and negative 0.7. So now we can really zoom in even more. Let's start at negative 0.8 and count by 0.01. Really zooming in on this thing. And here we go, between 0.76 and 0.75. And so if we were just asking to round it off to 2 decimal places, we would say our 0 is, looks like halfway in between them. So really either one would work. We could keep zooming in if we wanted to. We could change this to negative 0.76 and count by 0.001. And it's getting closer and closer and closer until right here is really 0.755 is pretty spot on. We could keep going closer and closer, but negative 4 to the times 10 to the negative 4, that's very, very small. So that would be a great approximation of our 0. All right, so see if you can use your table function on your calculator to find the 0 of problem 93. And that's it. That's the last one. Okay, we will go over these in class, but do your best to try to get these done.